And the technology which we will be talking about is the technology which gets implemented in data centers today for the data centers of 2020. So whatever people designing in software-defined networks, people designing in Dockers and Kubernetes will be affected by this technology. And the algorithms you are developing and accelerating will be affected by this technology. So I'd like to welcome Stephen Bates, and the floor is yours.
Thank you very much. Thank you. Thanks all for the invite. Thanks everyone for coming. I don't even think I'm the most expert person in the room based on some of the people in the audience, but we'll give it a shot. I'm going to talk about NVM over Fabrics. You know, it's a pretty relaxed environment here, so let's keep it open. Feel free to jump in with comments or questions. I know there's a lot of experts in here. I'm Steve Bates. I work for Microsemi. I'm a senior technical director there. I do a lot of kind of outward-looking stuff, and I've been very involved with the merging of NVM Express with RDMA. There's an equation I formulated probably 2 years ago, which was NVMe plus RDMA equals awesome. And you know, the fruition of that has been the emergence of the NVMe over Fabric standard, which provides distance and scale to the NVMe standard, which is becoming the de facto way to talk to non-volatile memory. So NVMe initially was based on direct attached storage over PCIe. It's becoming very ubiquitous. We're starting to see a lot of servers ship with NVMe. I know there's some storage guys here, E8 an example, very, very focused on NVMe. And what we've done is basically extended the reach of NVMe by providing the ability to take NVMe commands and putting them over a fabric, and then providing distance and scale through that. And I'm going to talk about that at quite a bit of time. My employer insisted I put in some slides. I'm going to jump through these. The only one of interest is we are pretty big in data centers. So Microsemi does all kinds of stuff. I don't even know how much we do, because it's very wide. We do have some pretty cool customers: Google, HPE, Dell, IBM, Huawei. These guys are all in the storage space, and that's a market that we serve. Two of the things that we do at Microsemi that are probably slightly relevant to tonight is we do NVMe controllers. So people who build SSDs, public knowledge, people like HDST, people like Memblaze in China, people like OCZ, Toshiba. They build SSDs, and the chip that's in the heart of that SSD controller is actually provided by us. It's a multi-core, Tensilica-based family of devices. You write your code on our chip. Your code does whatever you want it to do, and our chip talks to flash and then presents NVMe to the host. Right? So we have a whole pile of customers. We also have hyperscale customers who I'm not allowed to name, who take that same chip and they'll do a PCIe-based SSD. They don't typically adhere 100% to the NVMe spec because they want to do their own secret stuff, but they build SSDs using those controllers. And that's pretty exciting. So NVMe is a big thing for us. And then the other thing that's probably relevant to tonight is we do PCIe switches. So the two companies that are doing Gen 3 switches are us and Broadcom. And our switches are very, very targeted towards storage. So we have some companies here, DSSD at the back there. That's public knowledge that they use some of our technology in their products. And I know there's some other kind of all-flash array guys, people here. Some of them will use our product, and some will use Broadcom. But this is relevant to PCIe over Fabrics because if you want to provide connectivity to this big box of flash that's got NVMe and PCIe switches in it, then you're probably going to start looking at things like RDMA in order to do that. Right? So I'm not going to dwell too much. This is not a product pitch. There's a slide on some of the other stuff that we do. But the equation that we're all here tonight for, the thing that we're all here for is this very simple equation. It's got no derivatives, it's got no integration, it's got no partial whatevers. NVMe equation, RDMA plus NVMe Express equals all. Very, very simple equation. We're taking two very cool technologies, and I'll talk about them both a little bit, and we'll put them together and we get awesome. And this is obviously the Lego movie. Everything is awesome when you're part of a team, and RDMA and NVMe are part of a team in this one. So I'm going to start by talking a little bit about just the NVMe over PCIe spec. It's important that we get a little bit of that base knowledge, and then we can move from there. So standardization began way back in 2009. It's no secret that Intel have been a very big proponent of NVMe, right? They saw SATA and SCSI as kind of legacy, and to be honest, part of it was that that's not an area that they were particularly interested in participating in. They started providing more and more PCI lanes directly out of their processors. I think the latest Skylake Xeon processor will have like 29,000 PCI lanes out of it. That's not actually true. I mean, thank you. Somebody,
not 20,500.
That'd be one hell of a pinout, right? But they're providing more and more PCIe lanes directly out of the processor, and that avoids having to go through the PCH, the kind of the controller hub chip, which is often the secondary device on a Southbridge complex. So it gets the SSD, it gets the non-volatile memory very close to the processor. I'll talk about that in a little bit. We've also been very involved right from the start in the NVMe spec. So Peter Anufric is a fellow at Microsemi, formerly PMC, formerly IDT, and he was also one of the kind of grandfathers of the NVMe Express spec, right? And obviously I work very closely with him on things related to this standard. The spec is publicly available. You don't have to sign up to get it. So anyone who wants to can go to nvmexpress.org. You do have to be a member if you want to participate in revs to the standard. So basically, if you wanted to be involved in defining the fabric spec, you would have had to be a member and participate through the technical working groups, right? So it works like a lot of kind of standards. But the great thing is that once the spec is public, it kind of gets thrown up on the website and anyone can go look at it. And you can do that today for both the PCIe 1.2 spec and also for the Fabrics 1.0 spec. NVMe has been tuned for performance. Like I said, it's very memory semantic. It's all about pointers to memory, SGS, scatter gather lists, DMAs. It tries to be quite lightweight. It tries to take advantage of multi-core. So it tries to actually acknowledge the fact that we've moved away from Moore's law and just putting one core really, really fast, and we're now doing, tiled out many cores in a NUMA. And it tries to do things like affinity between the processors that are generating the I/O commands and the SSDs that are processing those commands. So that's true for both the queues, that I'll talk about in a second, and also the interrupts that are used to acknowledge the completion of I/Os and the conclusion of them. Right? It also has great support in quite a few operating systems, and I'll talk about that in a minute. So NVMe is pretty good in terms of controlling latency and latency outliers. At the end of the day, if you go and do a read from an SSD device, part of the time taken will be the media, right? And you're not going to get around that. Even if you had a very lightweight protocol, if NAND takes 100 microseconds to read, you're not going to do better than 100 microseconds, right? But you can take away some of the things that are in the stack. And where that gets even more important is when we go from NAND to Optane, right? Where Optane has maybe got much, much less than 100 microsecond random read times, right? So, for NAND it's interesting. For next generation memory technologies, it's incredibly interesting, right? To have a control. And it's not just the average latency, it's the percentile, it's the distribution of latency. I go into the hyperscale guys, and when I talk to them about latency, they're like, average is important, 99th percentile is important, 99.9 percentile is important, 99.99 percentile is important. Our customers use us because we provide them with very good SLA service agreements, and we have to adhere to those. Very maniacally focused on what we call outliers. Okay, I do 1 million reads, what's the worst read? Okay, things like that. Very important for these guys. The other thing is number of lines of code and off CPU time associated with the I/O. If I issue an I/O, how many lines of code do I have to execute in user space or kernel space or a mix thereof in order to get my instruction done? And then also how much time am I spending in spin locks, right? Things where I'm not actually necessarily executing code, but I'm actually waiting for the I/O to be serviced. So on CPU time, off CPU time, all very interesting. NVMe is very efficient, right? So it can be good for that. This is back to the last part. If you're doing PCIe, you can connect directly to the Xeon or or ARM or whatever it is. Most of these devices now provide lots of PCIe lanes. On an x86, if you want to talk SATA or SAS, you have to go through either a host bus adapter, which we can provide to you, or you go through the PCH device. And this is probably, it could be PCIe or DMI. So again, kind of recapping, Linux support is great. We actually have a couple of people in here who've thrown quite a lot of code into this part of the world, so it's nice to see them here. But there's a lot of people who've thrown code at the Linux driver for NVMe and the block layer in general. You can see that there's a pretty exponential ramp up in Git commits, which is the way that we track progress in the Linux kernel related to NVMe. So lots of work there, and I haven't actually updated this recently, so I should, because there was an awful lot of code came in over the Fabric stuff. So before we jump into Fabrics itself, I think it's important, if we can, to try and envision what happens when I do an NVMe command. Okay, so I'm going to kind of walk through an NVMe command. This is a PCIe based one, but a lot of this is going to be very useful when we start talking about Fabrics. So really, there's 5 steps, and I'm going to go through them. I may even act it out a little bit, so bear with me. An NVMe command is just 64 bytes of data in your memory. That's all it is. Okay, the spec defines what the fields are in those 64 bytes. It defines whether it's a read or a write, whether, what LBAs are you reading or writing. It defines where is the pointer to somewhere in memory that the data is going to be either placed or taken from. And basically what the driver does is takes somebody's request to manipulate a file or somebody's request to do a direct access on a block device, and they turn that into 64 bytes of data that the NVMe drive will understand. Very simple. Then what you do is you put that 64 bytes on what we call a submission queue. Right? That submission queue will be somewhere in your host memory space. Right? It's going to be physical memory, not virtual memory. It's going to be tied to some location in DRAM, and you're going to put it there, right? And you're going to put it at a certain place based on your queue structures that you've built when you first set up the driver. Then what you do is you do a PCIe write, and you do it to an address that the drive told you earlier is the doorbell for that submission queue. So step 2 here is basically the CPU going, hey, rather than doing a memory write to system memory, I'm going to do a memory write to a location that's in I/O memory. So basically the memory write comes out, it goes to the memory system agent, it goes, this is an I/O address, I'm going to go out PCIe, I will do a PCIe TLP, that will go to the SSD, bang, ding dong, there's a new command for you, and it's at this location on this submission queue. All right. The SSD then has the capability of generating PCIe commands itself, and it does a read. It basically goes, oh, there's a new command, I better go get it. Can I do a 64-byte read to this address? And so it issues a PCIe TLP read to that address. It pulls in the 64 bytes, right? So it gets a response. That response is the 64 bytes it asked for. It opens up the message and it goes, oh, it's a read. It's, these LBAs. It's maybe a scatter-gather list, or maybe it's a PRP or whatever. But basically it gets the knowledge that it needs to go, I now know where to go on the NAND to go get the data, because I know where all the data is stored. And I know where to put the result. I'm going to push it to somewhere in memory, and the command tells me where. Right? So step 4 is basically go to the NAND, read the NAND, write the NAND, whatever, manage the NAND, okay? It's doing whatever it is it's doing there. And because this is quite a large amount of data, because it's maybe 4K or 8K or 64K or whatever, rather than just pushing individual TLPs, we set up a DMA, right? Direct memory access. Very efficient way to move a lot of data. So what we do is we take the data and we either pull it from memory if we're writing to the SSD, or we push it back to memory if we're reading something from the drive. Okay? So you'll basically do that, and the data will go back to DRAM. And then the last thing you've got to do is tell the host that you're done. All right? There's different ways that you can do that, but one of the ways that's commonly used in computer architecture is an interrupt. Right? So we have various forms of interrupt. The drives, when they're first plugged in, will tell the host what they support. It might be just very old interrupts, right, which is physically toggling a pin. More likely it's MSIX or MSI, which is using a PCIe TLP to a certain hardware-based address that's going to basically trigger the interrupt handler for that processor. Right? That interrupt fires. Sometime later, the scheduler goes, oh, I got to handle an interrupt. It wakes up the context. The context goes, oh, I'll go and check the completion queue and I'll find out what actually happened. Right? Another way to solve that problem is to pull. You can have it so that the SSD will push a memory location, and you basically have a CPU that's just spinning on that memory location. Okay? That's going to be faster, but it's consuming an entire hardware thread to do that. And in fact, there's some pretty cool stuff happening in the block layer right as we speak around polling, worth checking out, and we'll ask about that later. I'm not going to get into this, but if you go to Olga and get one of her great analyzers, this is some of the data you might get to it. I think this is actually from one of her competing products, but never mind. And this is the anatomy of a single NVMe command from here to here. So this is me, submission queue, ringing a doorbell, pulling in the data via DMA, raising an interrupt, and then handling. Okay. So that's NVMe, right? That's PCIe NVMe. And now what we're going to do is start looking at NVMe over fabrics. So this is very useful to have us in the back of your head as we go to the next step. But now what we want to do is go, okay, so NVMe until now is all about communicating to a device that was directly attached to me over PCIe. Now I want to actually communicate with a device that could be way over here, long way away, right? And we're going to talk about how we do that. So we're going to have a fabric, and the fabric I'm going to concentrate on is RDMA. There is another fabric, fiber channel, that we can use to do this, but tonight I'm going to focus most on RDMA. So we need to know a little bit about RDMA. And again, I'm probably not the most expert person in the room because I see some people from RDMA companies here, but RDMA is a combination of hardware, operating system level code, and user space code that really at its essence enables highly efficient memory accesses at distance and scale. It allows me as a client somewhere over here in the world to go and fiddle with bits that are in a memory space on a remote server somewhere else in the world. That's at an essence is what RDMA is all about. It provides the security protocols that you need to do that. It provides access control, whether I can read or write or do other things to the memory. It provides systematic ways of providing fencing and registration and so forth. But at its very essence, the thing it's trying to achieve is to allow server A to manipulate memory locations on server B without server B necessarily even having to know that it's happening. All right? Because I can come up with a protocol over TCP/IP, for example, that changes memory, right? That's pretty straightforward, right? I'll just amend a protocol, I'll put it over TCP/IP, and I'll change memory. I could do it over squirrels. I could take a message saying, please change your memory location at memory X, give it to squirrel, squirrel could run down the street, and the problem is the squirrels are very slow, all right, and they're very inefficient, right? I'm trying to, it's kind of a joke. Worst joke ever.
And they could be
distracted. I mean, the squirrels could get lost.
I get it, yeah. Run over by cars.
Focused on nuts, run over by cars, exactly. So, and that actually is a very good point, because if you're going to start changing memory in other people's systems, you want it to be reliable, right? Because it's one thing to screw up certain things, but if you screw up someone's virtual memory, if you change the wrong memory locations to the wrong values, you have very, very bad things happen. So you've got to be very careful with that. RDMA it got a very standard programming interface. There's a lot of different protocols underneath with which you can do RDMA, and I'll talk about those in a little minute. But from a programming perspective, the great thing about RDMA is it's pretty consistent. You get a set of verbs. Those verbs are going to work in a certain kind of way. And as long as the hardware vendors underneath are subscribing to that RDMA API, you know that everything's going to work. Okay? Those different physical layers can sit on top of a variety of different transports. So we have people represented here from Mellanox, and there may be some from other companies. Mellanox provide offerings in both the InfiniBand space and the Ethernet space using what's called RDMA over converged Ethernet, V1, V2, V7, V9. Chelsea and Intel are both providing solutions around TCP/IP, so providing RDMA over TCP/IP using something called iWarp, and then they use TCP/IP offload engines to avoid the servers themselves having to do the TCP/IP decapsulation, right? So it's trying to keep everything very low latency and very light touch. Intel have a new offering called OmniPath, which has some issues around RDMA compatibility right now, but they may get there in the end. And like I said, you could run RDMA over other things as well. Right? It was, like many things, initially developed for high performance computing, and basically we're stealing it from them and adapting it, and now it's becoming very popular in data center environments. The reason people like it is it lets you move a lot of data without necessarily consuming a lot of CPU time. Right? And at the end of the day, if you're running a business that's selling virtual machines to the public so they can run their services, you want those CPUs running those services. You don't want those CPUs running TCP/IP. You don't want them running block layer stack. You want every single cycle that you can possibly get away with servicing your paying customers. And so RDMA makes sense for these people because it means that they can move data much more efficiently and with much less CPU time. The downside is that an RDMA capable NIC tends to cost more than a non-RDMA capable NIC. You're making a trade-off. You're making a decision to take something that could be done on a Haswell or a Skylake and moving it to dedicated hardware. Right? That's a trade-off. It's a trade-off people seem to be willing to take. So how does RDMA work? Well, really, what RDMA is trying to do is move data from here to here. So we've got two servers, a client and a server CPU. They both have RDMA HCAs. I call them HCAs, sometimes I call them NICs. So excuse if there's any confusion there. And really the way that it happens is this is a connection-orientated system. So it's not like you can just instantly go, I want to send some data. You actually have to communicate between the client and the server first and do essentially a key exchange to say, hey, are we cool? Can I get access to some of your data? Or sorry, some of your memory? And the server has to say, yep, I'm going to give you access rights to that, and those access rights may be read-only, right? They may have certain rules around them, and you will do a security exchange basically to go, okay, I trust you. We're going to go through some kind of higher-level security exchange, and you will get access to my memory. You don't give access to your whole memory, right? Typically in RDMA, you will basically pin a region of memory. Get user pages or whatever, you will basically allocate some memory and say that memory is dedicated for this particular communication. That in itself is a problem because you are giving away physical memory, and that's physical memory you can't use for your standard memory pool. So you are giving away a very, very valuable resource. There are some technologies that get around that. One of them is called on-demand paging, which is very interesting, something Mellanox are doing. But it does come at a price. So it's a little too detailed to get into right now, but if you buy me a beer afterwards, we could certainly talk about that. But the idea typically is you pin some memory, and that becomes what's called a memory region. And what you do is you say, okay, client, I'm going to give you access to this memory region. You will be able to write and read to this region, but to do so, you will have to provide me with a key that I'm going to give you, and you'll have to provide me with offsets within that region. I'm not going to let you write outside of that region. I'm not going to let you read outside of that region. You only own that region. So, if you go, I actually have some very simple, as I was learning RDMA, I wrote some very simple examples, and those are freely available on GitHub. So if you're interested in kind of playing around with RDMA a little bit, you can actually go and do some of this stuff yourself. And the idea then becomes that once you've done this connection establishment, this client now has the ability to write and read data to this particular yellow region of DRAM. And it doesn't even need to wake up the server CPU to do it. Because what it's going to do is it's going to issue requests to the HCA, and they're very like NVMe commands. They're like, can I please write some data to the memory region number 7 that exists on server number 43? That's kind of how it works, right? And this HCA will know where server 43 is over IP or Ethernet or whatever, and it will send the request encapsulated in the, the physical layer network. When it gets to this HCA, he's already got rules set up on what DMAs he's allowed to do, and at the end of the day, he will just do a DMA. And the DMA doesn't even wake up this server. The server doesn't even know the memory has changed. Now, of course, like I said, that could be very dangerous, but it's also very powerful. All right. So this guy is actually basically providing a region of memory that this guy can change without this guy even knowing. Right? So that's the kind of kernel bypass kind of offload. So this guy is doing some work with his CPU, but this guy is not. The work is being done by the DMA engines and some of the state machines that run in here. Okay. So who offers RDMA? This is a little bit out of date. I haven't got the 2015 numbers yet. John Kim is here, so maybe he knows how many HCA or RDMA capable HCAs were shipped in 2015. But in 2014 we were at 6 million, and I'm sure the number was a lot bigger last year. InfiniBand, Mellanox is a major vendor there. The pros and cons, I think we could again argue over a beer, because some of this stuff is not necessarily. It's very subjective in some ways. Asking people what their favorite flavor of RDMA transport is can be a very controversial start. Almost like asking who you're going to vote for next week in the presidential. Ooh, never. So InfiniBand has been very popular in high performance computing. There are many people who would say it is the best. It's the one that's guaranteed lossless. It's got great QoS. It's certainly the one that's most prevalent in the really high-end HPC space. So if you go to look at the really high-end supercomputers, they tend to be more biased towards IB. But it is somewhat niche. You don't have a lot of vendors, and the switches have to be dedicated InfiniBand switchers, and those are not necessarily easy to get your hands on. iWarp, Chelsea and Intel, it's based on TCP/IP, which is great, right? Because TCP/IP works everywhere, right? It's guaranteed lossless, but it has some issues, because if you do lose, TCP/IP is an end-to-end congestion control and guarantee policy. So you can imagine if you do have congestion and packet loss, you actually have to go through the TCP/IP protocol, which is end-to-end. That can add a lot of latency. So that can definitely be probabilistic. The one that seems to be very popular right now in the data center space is variants of Rocky. There's multiple versions of Rocky, and people have their own twists on it. It's RDMA over converged Ethernet. So the great thing about Rocky is that it's based on Ethernet, so Ethernet switches can handle it. So you can go use your Tomahawk or use a Spectrum from Mellanox or a Marvell switch or whatever. There are certain features in the switch that can be useful from a scalability point of view, but there's a lot of different choices there. An OmniPath from Intel, it's a little bit newer. One of the pros is it's backed by Intel. Intel are a big provider. One of the downsides is it's backed by Intel.
Yeah. Doesn't SMB 3.0 use RDMA in some form as well?
Yeah.
Okay.
But again, it can run over different flavors of things, right? Okay. So it's something that uses RDMA. So it's actually above RDMA.
Oh, okay.
And there's other so we didn't maybe talk about that, but NVMe over Fabrics is like SMB Direct. It sits above RDMA and uses the features of RDMA. Okay. So it's almost like protocol stacking, right? I have a game called Protocol Roulette, where you spin a wheel and you get one protocol, and then you have to put it over the second spin. You can do it for anyone, right? So they do, these protocols all implement the verbs, which makes them very consistent.
Stephen, I would just add that Oracle has, so since this chart was made, Oracle has announced that they're offering InfiniBand adapters and switches. I don't know if they're actually shipping, but they've announced it. And then Cavium, through their QLogic acquisition, has announced that they support both Rocky and iWarp.
That's right. Yeah. So that's a good
point. Or will
point.
soon support it.
Thank you very much. And John, do you want to hazard a guess at what the shipments were in 2015?
I don't know. Actually, I just looked at some numbers, but I forgot. But they have been growing. They're not, maybe not growing as fast as Ethernet shipments, but InfiniBand shipments have been growing for the last couple of years.
Yeah, for sure. Thank you, John. That's a good correction. So, getting to NVMe over Fabrics, as the gentleman in the audience alluded to, what I've been trying to do here so far is stack some protocols on top of each other. And NVMe